Hello, welcome to this video. In this video, we shall be looking at the intersection of lines and planes. Now, first one, look at the intersection of a line and a plane. When a line and a plane intersect, they intersect in a point, and that point of intersection lies on both the line and the plane. Therefore, it must satisfy both the equation of the line and the equation of the plane. Let's look at an example to solve that. So, we must find the position vector of the point of intersection of that line and that plane. There's a simple way to go about this. We can start by writing the equation of the line in parametric form. That would be x is equal to 2 plus t in this case, y is equal to 3t, and z is equal to -1. Then we write the equation of the plane in Cartesian form. In this case, it's going to be 5x minus y plus 7z is equal to 9. And then what we do is we substitute the equation of the line in the equation of the plane. So where there is x, we'll have 2 plus t. Where there is y, we'll have 3t. And where there is z, we shall have -1. And we equate this to 9. And when you solve for that, you get your t as 3. So 3 is the value of the parameter, which when we substitute in the equation of the line, gives us the point that also lies on this plane. And so that point is going to be 2 plus 3, which is 5 for the x coordinate, 3 times 3 for the y coordinate, which is 9, and -1 for z. So it's going to be at 5, 9, -1. The question asks for the position vector though. So that's going to be 5i plus 9j minus k. And that's how you get the point of intersection of a line and the plane. Now to get the angle between the line and the plane, which is that angle indicated right there, we shall use the dot product of the normal to the plane and the direction of the line. You realize that the dot product of the normal to the plane and the direction of the line gives us the magnitude of the normal, gives the magnitude of the direction of the line, gives the cosine of the angle between the normal and the direction, which is in fact that angle theta indicated. But the angle that we want is the angle alpha, the angle between the line and the plane. But realize that alpha and theta are complementary angles, and therefore the cosine of theta is in fact the sine of alpha, and therefore we can get the angle between a line and a plane using the dot product of the normal to the plane and the direction of the line in this equation right here. Okay, now I want to look at the intersection of two planes as well. Notice that two planes intersect along the line as illustrated below. So how do we get the equation of the line of intersection of two planes? Let's look at this example. So what we're going to do really is consider the Cartesian equation of a line, which is usually in the form x minus x1 out of A is equal to y minus y1 out of B is equal to z minus z1 out of C. Realize that we have an expression in x equal to an expression in y equal to an expression in z. So if we can find an expression in x and an expression in y that are equal, and then find an expression in x and an expression in z that are also equal, then just equate them all together, we can get the Cartesian equation of the line of intersection of the planes. How are we going to do that? By elimination. So we can start by eliminating y by multiplying the second equation by 3, and then subtracting the first equation from it, which is 2x minus 3y plus 2z is equal to 5. When we do this, we get 7x, we have the y is eliminated, plus 10z is equal to 15 minus 5, which is 10. This gives us x as 10 minus 10z out of 7. So we have an expression, we have an equation relating x and z. Now we could go ahead and eliminate z by multiplying the first equation by 2 and then subtracting the second equation from it. This leaves us with 4x minus 3x, which is x. We have minus 6y plus y, which is minus 5y, and then 10 minus 5, which is 5. The z is eliminated. And so x is equal to 5 plus 5y. So we have an equation relating x and y, an equation relating x and z. And since it's the same x expression, we can just have it as one long equation to give us the equation of the line. So this would be our answer. Now, however, you might want to write this in a way that it's easy for you to extract a point that lies on this line and the direction of the line by making the equations of x, y, and z positive 1. So this would be y plus 1 out of 5, and this would be z minus 1 out of negative 7 out of 10. Now you can clearly see that the direction of this line is 1 out of 5, and negative 7 out of 10. However, you could also multiply each of those by 10, such that this is 10, 2, and negative 7. Realize that when you find the dot product of this direction and any of the normals of these two lines, you get 0, which indeed shows us that this line lies on both the planes because it's perpendicular to both their normals. That's how you get the Cartesian equation of the line of intersection, two planes. Okay, how do we get the angle between two planes? If these are our two planes right here, of course we're looking at them from the side, so we can't see the face of the planes, and these are their normals. Yeah, so we have this as n1 and that as n2. The angle between the planes, the acute angle, is that angle right there, theta. But we know that that angle is in fact this angle as well, since we have a cyclic quadrilateral that is formed, which makes this angle here alpha supplementary, both with this theta on the outside and this theta on the inside. So those two angles have to be equal. Yeah. And so the angle between two planes is in fact the angle between their normals, and you could use the dot product to find that angle using this equation right here. So from that equation, the cos of theta will be the dot product of the normals divided by the product of their magnitude, and that's how we get the angle between the two planes. There ends this video.